So I'm going to try to illustrate another way to evaluate definite integrals, and I'm going to use an informal proof, let's say. All right, so using rules for definite integrals. All right, so we know that this is the definite integral. It is the limit as n approaches infinity of the sum of all of the right Riemanns, right? From our first rectangle, that's what tells us it's a right, all the way to n, and n is approaching infinity. Right? We take that. This is the height of each rectangle, and this is the change in x. And if without the limit part, it's just an approximation. With the limit, as n approaches infinity, it's the exact value. All right, so now let's break apart this notation. All right, so these are the x values, right? This is what we did when we were finding the sum of the rectangles, when we were doing sigmas, right? We would, first of all, we would find our x value, and it would be our first value, right? So this is our first value plus the change in x, right? And that would be the first one we'd start with because this was a right Riemann sum. Right? So this is the first x value for the right Riemann sum. And by the way, you don't need to take notes on this unless you want to. The notation you need to know in terms of the definite integral, and I want you to follow along, and the ending part, all right, which will be in your notes. But I don't remember if I put this all in your notes in terms of writing everything down. And what I want you to get is kind of the gist of it. All right, so now we plug that into our function, right? But right, we would plug this into the function, so that's the x value, right? But what's this notation, right? This is the definition of the derivative. Well, why are we talking about derivatives when we're integrating? Well, if you remember, let's take this off. When we didn't have this on there, right, when we just had this part, right, when it was not the definite integral, right, we were finding whose derivative is this? All right, remember that fun game show we played? Dun, 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 dun. What function has that derivative? All right, so this little part here, that's somebody's derivative. When we integrate it, we're going from the derivative back to the original function, minus a constant that could have gotten lost, that would have gotten lost in translation if there was a constant there. Right? But this is the derivative. Well, what's the derivative? Well, the derivative, before we learned the differentiation rules, right, we learned the definition of the derivative, which is the limit of our function for some value, right, plus a change in x, minus the function at that same value where that change in x is going to 0. We generally wrote it as, actually, let me write the whole thing. The limit as h approaches 0, f of x plus h minus f of x all over h, right? That's the definition of the derivative. Well, this is the same thing with changes of x's instead of h's, right? So we're going to go from this step. Just hold out on that thought. So remember that inside part, right, is the derivative. And now we know that we had another way, right, to represent the derivative, right, was using the definition of the derivative. Now, the big F, right, that's our function. Little f is the derivative. So big F there is the function. Little f is the derivative. Another way to represent big F is to call it the antiderivative. It's what we, if we are starting off with the derivative, the function is what we get after we find the antiderivative. We go the other direction. Right? Hold that thought and let's come on over here to this page. All right, so the definite integral is the sum of all the rectangles. Notice that that there is the height of the rectangles at f of xk, and we've got it right over here, and we're representing this using the definition of the derivative. Because this is a derivative. Right? And so we have the definition of the derivative. We want to simplify this a little bit. So we're going to take it away from being a limit. We're going to drop the limit, so we'll put an approximation. Right? And we're going to multiply both sides by change in x. Well, heck, what does that look like? It looks, this is the same as that. Right? The sum of the rectangles times the change in x, which is the width of the rectangles, right? So the sum of the rectangles, this is the height, and this is the width. And that's our Riemann sum, which is the area under the curve. And when it's the limit of that, then we get to the exact area under the curve. Right? But just kind of notice this kind of connection here, and that maybe hopefully will help the final answer make some sense for you on why we can do that. Right? So next and previous term. So this back here are, let me go back for one page. All right, so since we have the f of x plus 1, we just replaced, I forgot to mention that. So here we have xk plus change in x. Well, that's our first value. This is our next value, right? And this is the previous value. So the f of xk is the value. This is with plus a change in x. So now we're going to just make a little substitution here. And k plus 1 means it's the right one, right? So this would be the right and this would be the left. This would be the next value, in other words, and this would be the previous. Just want to connect the notation. All right, so we've multiplied both sides by the change in x, and let's move that up a little bit. There we go. So next and previous. All right, and so now we have this. So now let's figure out what that is. All right, so the first rectangle would be next would be second. And so the first rectangle is the second value minus the first value. And so notice that this is the big F. Big F is antiderivative. Little f is derivative. So when we're evaluating and under, we have, it's the derivative, right? That's the derivative and the integral, the same thing, right? It's under that, our integral sign, right? So it is approximately the antiderivative for the second value minus the antiderivative for the first value. And the second rectangle is the third the antiderivative evaluated for x3 minus the antiderivative evaluated for x2, and so forth and so on. All right, so notice that it's the next and the previous until we get to the last and the previous to the last, whatever k is. Well, notice they all start canceling each other out, right? Because we have an x because we want not just 1, 2, or 3, or 4. We want an infinite number. So notice that the first and second rectangles, the f of x2 cancels, and the third and the second and third, the f of x3 cancels, and so forth and so on. And all we're left with is the antiderivative evaluated for the last value minus the first value. Notice these are our two endpoints. So let's just write antiderivative evaluated at the endpoints. And now that's going to give us another way to find the exact area under the curve. And I'll sort of prove it by showing you, hey, we're going to get the same thing from the limit of the right Riemann sums as you would get if we integrate and evaluate. So all of these are equivalent, right? So, and you should definitely know all of these are equivalent to one another, and these are all definite integrals. You should be able to evaluate using the limit of the Riemann sums, and this is the right, because it doesn't say k equals 0, as n goes to infinity for certain functions, right? If we've got x squareds, x cubes, x's, or constants, then we can use that. The problem is that I don't have a power sum rule for you for sine and cosine and natural log and e of x and all the other ones we could come up with, right? But we don't have to be able to use the limit of Riemann sums all the time, right? Because we have another way. Right? The limit of Riemann sums gives us the definite integral. Boy, that is a bad spelling on definite integral. I put definite integrate. What the heck is a definite integrate? One's an adjective and one's a verb. They don't go together. This is the limit of the right Riemann sums as n goes to infinity. This is the definite integral. And this is the antiderivative evaluated at the endpoints. And they are the same thing. So now we have another way to be able to evaluate a definite integral, and that is to integrate and evaluate. And when we integrate, we are finding the antiderivative. It was, if you remember from the last week's lessons, which were all antiderivatives, it was what function has this as its derivative? Well, that's what we're doing. Whose function is that derivative? And that's integrating, and now we're going to evaluate though. All right, so we'll continue on this one. Wasn't sure if I was going to break it up, but now we're going to keep going. So we're going to calculate this one though as the limit of a right Riemann sum, because I want to make sure that I connect it with some actual problems before I end this video. Calculate as a limit of right Riemann sums as n goes to infinity. Right? So our first step is to find x. Find our change in x. Let's do the change in x first. Then we'll find our x values. Change in x is 2 minus 1, because we need that for our x value anyway. 2 minus 1 divided by n, so that's going to be 1 over n. Step number 2 is our x values. Right, so that's going to be our starting value, which is 1, plus the change in x times j, because we've got j of them. Our third step is to substitute the x values into the function and simplify. Right, so that would be x squared. So it's 1 plus 1 over n, oops, squeeze a j in there, j squared. Okay? And let's take care of that. So that would be 1, so it'd be 1 plus 1 nj times 1 plus 1 nj. If you want, I'll write it below real small. 1 plus 1 nj times 1 plus 1 nj. All right, so we've got 1 times 1. We've got 1 nj plus 1 nj. That's 2 over nj. And then 1 nj times, oops, 1 nj would be 1 n squared j squared. All right, so now let's do the Wright-Riemann sum. Didn't forget R of n this time. R of n. Right, so it's our Wright-Riemann sum now with n subintervals. So what that notation means, right? That R of n, it's the Wright-Riemann sum with n subintervals. Right, is 1 over n times sigma. And then we have 1 plus 2 over n. So j plus 1 over n squared j squared. There we go. All right, so now let's split the Riemann sum. So R of n equals 1 over n sigma, and that's j equals 1. So we're starting after the first one because this is a Wright-Riemann sum over n, and that's a 1 plus 1 over n. Everybody gets their own sigma. J equals 1 to n, and that is 2 over nj, and plus 1 over n sigma from j equals 1 to n, 1 over n squared j squared. Oops, that j is looking a little low. Well, let me move the j up just a tad. I don't want you to think he's in the denominator, because he's not. There we go. Now you couldn't possibly think that. All right, so now let's simplify. So split the Riemann sum and simplify. Let's just keep going here. All right, so R of n equals, actually, no, I'm going to make that a separate step. So we have that. Oh, it's fine, actually. It's fine. So I will write it as a separate step because I don't want you to get mixed up at all. So after we separate, right, we factor out the coefficients. And that's what I meant by simplify. Factor out coefficients. I was going to leave off writing this out, but I don't want to confuse anybody. All right, so R of n equals, can't factor anything out here, so 1 over n sigma, j equals 1, plus, we have the, we can factor out the 2n, so that would be 2 over n squared sigma, j equals 1 nj. Right, and on to the last one, and that would be the 1 over n squared can come out. So that would be 1 over n cubed sigma, j equals 1 n and j squared. And I'm hoping I can fit it all in. We're up to the power sum rules. We have 2 steps, power sum rules and limit. I can always expand the board if I need to. Power sum rules for the sigma. All right, so we have the 1 becomes 1 over n times 1n, which is n, plus, maybe I should write it like this. It's getting lost there. Plus the 2 over n squared times, so the j would be n squared over 2 plus n over 2, and then the j squared can we fit this in? Will be, well, I'm just going to continue down here, I guess. Yeah, we're definitely expanding the board. 1 over n cubed times, and that would be n cubed over 3 plus n squared over 2 plus n over 6. All right, so now let's just distribute, oops, and let's try to get more space. Come on, my board. Nope, it's just going to make dots down there. How about if I do it from the computer? And now I have the problem of the cursor has gone into hiding. Here it is. There we go. Now I've got a little bit more space. All right. So now we'll distribute 1n times n, that's 1. I'm just going to do this, not to be confusing with the step over to the left there. So this would be n plus, now we're going to distribute 2 over n squared to both those terms. The first one, the n squareds, the 2's will cancel. Oh, excuse me, that's not n, that's a 1. Sorry, not n, 1, 1, 1. So we have a 1 plus a 1. 2 over n squared times n over 2 is going to be plus 1 over n. 1 over n cubed times n cubed over 3 is going to be plus 1/3. 1 over n cubed times n squared over 2 is going to be 1 over 2n. And 1 over n cubed times n over 6 is going to be 1 over 6n squared. Our next step is to take the limit, right? As n approaches infinity. So the right Riemann sum for n subintervals is equal to the limit as n approaches infinity of 1, or let's make that 2. Why don't I want to combine like terms? I don't know. 2. I'm fine with just leaving this as 1 over n plus 1 over 2n. They don't have the same. Oh, why don't I combine the 2 ones with the 1/3? All right, try that one more time, combining like terms. 1 plus 1 plus 1/3 would be 3/3 plus 3/3 plus 1/3. That would be 3/3, 6/3, 7/3. There we go, 7/3 plus, I'm just going to leave this as 1 over n and 1 over 2n because I don't care enough to get a common denominator, because it really isn't going to make any bit of difference. 1 over 6n squared. Okay, now we have everybody. And of course, that would be equal to 7/3 plus 0 plus 0 plus 0, right? That's one of our rules we learned for limits, equals 7/3. So there we found the exact area under the curve as a right Riemann sum. And you need to be able to do this. All right? You need to understand it, because limits are the basis for everything we do in calculus. So you do need to be able to understand it and be able to do this one as a right Riemann sum. But then you also need to be able to do a shortcut method. Just like you needed to be able to use the definition of the derivative, and then later on use a shortcut method and be able to do either one of them if I ask. All right? So now let's use the shortcut method on the next slide. As soon as the page turns, there we go. All right, so now we're finding it using this principle. So we're going to integrate, which means find the antiderivative. And evaluate. Now, I will tell you right now, remember when we were taking the antiderivative, we had to put the plus c part in? I'm not going to put the plus c in, and then I'm going to explain it a little later on. And I'll show you with the plus c's, and you can see you didn't need the plus c's on the definite integral. If you don't put it on the indefinite integral, it's wrong. On the definite integral, it's just an unnecessary step. All right, so now we're evaluating. X squared is the derivative because that's what function that we're given. So to be able to use this rule, we have to find the antiderivative, and then we're going to evaluate, and let me not put a's and b's in there because we have our limits. Our limits are 1 and 2. All right, in dx, right? Because you have, that's your change in x. This is your height, and that's your width. All right, so whose derivative is x squared? If you remember, we undo the power rule. All right, so to undo the power rule, we have, actually we get x. Come on, erase, 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 erase. Thinking of the exponent before I'm writing down my base. There we go. We have x, and let's try it again. We have x, there we go, and whatever, now we have lots of x's. Whatever the exponent is, we add 1, and we divide by the same amount. Right? That was undoing the power rule that you learned in antiderivatives. So we're going to have x cubed, because that'd be 2 plus 1, divided by the same thing. And this is how we're going to write it when it's a definite integral. That's why I'm not putting a plus c in it, because it's a definite integral, because this is a number. It's evaluated from 1 to 2. And now we're going to plug in. All right, so this would be, and we go larger minus smaller. All right, so top minus bottom. Right? It's whoever's on top minus whoever's on the bottom, even if they were not in terms of larger and smaller. Whoever's on top minus whoever's on the bottom. So we have 2 cubed divided by 3 minus 1 cubed divided by 3. And now 2 cubed is 8/3 minus 1/3, which is 7/3. The same answer we got using the limit of the right-Riemann sum. So here you can see that we really do have another way. My little proof there, so if you got the gist of it, that, hey, this is the antiderivative and we're evaluating that at the endpoints, that's going to be the same as the limit of the right-Riemann sums. And yes, it is less work to be able to integrate and evaluate, as long as you can integrate and evaluate, right, than the right-Riemann sums. But I want you to be able to do both. Which will you do more often? You will more often integrate and evaluate. All right? But if I ask you to find it using a limit of right-Riemann sums, or you're asked to show something using a limit of right-Riemann sums, right, then you need to be able to do the steps. And you definitely need to understand the notation so that when you see, let me go back to the, hey, these 3 are all the same thing. What do each one of these mean? Page, which is right back here. You definitely need to know the notation so that when you see it, you can explain the notation. And if you have questions on the notation, right, then make sure you ask me. You're going to see a lot more, though. You'll see a little bit more of the limits of Riemann sums, right, but you're going to see a lot more of the definite integral, and then we change that to the antiderivative evaluated at the endpoints, right, in this lesson. And then in the next lesson, you won't see the limit of Riemann sums at all, and after I finish this entire PowerPoint. All right, so thanks for watching, and now we're going to do another problem, but it's going to be on the next video because I'm almost at the 30-minute part. 30-minute point, and so I'd like to stop this video right now. All right, so bye for now.